Hello everyone once again. This session is going to be about power and energy, and it's a privilege to have Professor Kirk with us. Professor Cameron is a pioneer and leading expert in green computing, and he's also co-founder of Green 500 and Miserware, which is a company, which is a startup that works in energy efficiency of clusters. He's also a co-founding a founding member of Spec Power, and his advanced power measurement software infrastructure by the name of PowerPack is very famous, and he also has this software by the name of Granola, which is very famous for the energy and power efficiency, and which is being used by a lot of people in a lot of countries. And I won't take much more time and take time off from his presentation now, and I'll let him give his talk.
Thank you. Thank you
very much.
Okay, great. Well, thank you for having me. Can you hear me on this, or am I just, this is useless? Okay, it's doing something? Okay. Thanks very much for inviting me, Sanjay. It's a pleasure to be here. I've actually never been here to UIUC campus, so it's wonderful to see a great campus that when I was a grad student, I remember reading all the papers that came out of UIUC, so it's really great to be here. I'm here despite the fact that I seem to have fractured a toe on Saturday, so if you see me limping up here, you know why. I don't have any other injuries other than those. But and I should acknowledge the National Science Foundation has funded my work very, very well over the last decade. So I have a lot of, these are some of the recent grants that we've been doing, and you did a great job of introducing me. I like to throw these things up there just because it means that I have a bias, right? So I have a bias based on the things and experiences that I've had related to all things green and all things HPC. I have all the things that he mentioned that I've done, and so I won't go through them again. This is a slide that I put together in 2002, 2003 timeframe. Actually took part of 2001, 2002 to actually write this slide, and it's not really accurate anymore. I mean, it is accurate still, but it's not really that relevant anymore. But this was what motivated me to do the work that we've done over the last decade. And basically, what it amounts to is it's a typical plot that you'd see of any given year in any HPC environment of the top 500 impact scores and how they scale over the years on the x-axis. And there's this efficiency gap, and that was widely known. What was less known at the time was that we were on a really bad trajectory when it came to power. And so all of my work since then has been on trying to figure out how we can keep ourselves from creating supercomputers that consume hundreds of megawatts of power. And so so I'm really proud of this figure. It took me a long time to put the data together. I still get to use it 10 years later, which is nice just because I refer back to it. But it shows you what we were looking at the time. And I could draw a similar graph today if I was trying to do, and I've seen graphs like it for exascale. So exascale is an interesting problem, right? It's the fact is that in the last 5 years, or the 5 years prior to this year, we basically went up 6x in flops per watts. And you may disagree that flops per watts is a good metric or a bad metric. It doesn't really matter. It is a metric, and we can track trends by it, which is all I'm doing here. In the same time period, we went up about 2.5 times in the total power consumption. So even though I would argue that we've gotten more energy efficient as a community during that time period, we've still have increased the average amount of power that a typical high-end supercomputer consumes, high-end being the top 10. This is based on top 500 LINPACK scores, yeah. I have other data I can show you. There's an article that I did for IEEE Computer about a year or two ago that has a lot more data than I'll show here. And I know Wu has slides like this too, and other people too I've seen. So basically, you take these numbers, or any variation of these numbers, you'll still get the same answer, which is that you project out how good we can do if we had the same kinds of improvements over the next 7 or 8 years to see where we get. And if we do that, we get to a 1 petaflop system in 66 kilowatts, which is pretty significant. We get to an exaflop system in 66 megawatts. But our goal, of course, is to get to an exaflop in just 20 megawatts. And so we don't hit that goal. And keep in mind that these efficiencies include, the efficiencies that we've seen in the last 5 years include the, what I would say, sort of paradigm shifting movement to GPUs and accelerating engines as commonplace, which are very efficient from a compute per watt standpoint. And so we need that kind of innovation to get to 66 megawatts. We need a lot more innovation to get to 20 megawatts. So the conclusion, I hope, that you have is the same as mine, is that we need a lot of help. We need a community effort on this. It's not going to come from one or two people. And so what we've been trying to do over the years is trifold here. So we've been trying to figure out exactly where energy goes, first and foremost. And when we started the work almost 10 years ago, our first question was, how is energy spent? Right? How is it used? And the second one is, well, what happens when we scale things? And what happens to the energy use as it scales? And does it scale, for instance, linearly? Is it super linearly? Is it something else, exponential? And lastly, are there things that we can do to improve our energy efficiency? And we've taken some of these steps over the last few years. And so today I'm going to talk about, I can't talk about all the stuff that we've done, there's just no time, but I have sort of a map of the things that we've been working on. And they're grouped, everything is focused on improving what I call power performance efficiency. And we've done things like model optimized performance, which plays a role, model the effects of power, which plays a role, and I'll talk a little bit about that today, optimize for the effects of power, which I won't talk about a lot today, but I'll talk a little bit about, and profiling. And I want to start with profiling because I think that this audience in particular, I do travel around a lot, I do talk a lot about the work we've done, and I would say I would love to talk to you about my models all day, I would love to talk to you about our optimization efforts, my company, other things, but the thing I get asked most about is how we measure things. And it's because for your own selfish reasons, for good reason, and the reason that I think you want to help is that you want to take your work and you have great ideas and you want to validate them on these kinds of systems, and you don't have the tools to do that. And so we've created, as a byproduct of what we've been doing for energy efficiency, a tool chain that is quite useful to people who want to go out and do energy efficiency research. So with that, I show this cartoon, which actually, before I put the Virginia Tech in there, it says government, right? I'm from the government, and I'm here to help. But it's interesting, you know, I want to basically try to help you help us, right? So if I'm a member of this community that is trying to get things to be more energy efficient, I want to show you how you can do your research and help us out, right? And Peter Drucker is actually credited with saying you can only manage what you can measure. This is what measurement looks like in the good and the bad sense. So it's a little not quite dark in here, but this is a older Beowulf cluster that we tore apart so we could do the first version of our PowerPack infrastructure, which I'll talk about at length in the next couple of slides. That is a laptop on fire. That's to remind me that you can do damage doing this. And when I first presented, about 2005 or 6, I went to Oak Ridge and I showed them a picture like this, and I remember one of the hands went up and said, "Do you want to do that to our Cray?" Oh, we're going dark here. "Do you want to do this to our Cray machine?" And I said, "I think it might void the warranty." Right? So we don't do this on you know, $300 million supercomputers, but we don't have a problem doing it to a $2,000 or $3,000 node. It seems. It's okay, Sanjay. It's all right. So PowerPack is the toolkit that we use to do our power measurements, and it's been published in a couple of places. The one if you want a detailed down low-level view of what's happening inside PowerPack, look at the TPDS paper from 2010. If you want a high-level view, look at the IEEE computer paper from 2005. And then if you want to download some of the software or look at some of the software diagrams and stuff, look at that the web link up there. And if you want to use it on my machines, send me an email. Which is what most people do, honestly. Basically, PowerPack is software with a hardware component. The hardware component are the meters that actually do the measurement, and then we built the software infrastructure around it to allow us to take the measurements. And the challenge that you'll find when you set out to do this work is the same one we had, which is I've got all this power data coming from the system that is out of band with the system. It doesn't actually have any correlation to anything that's happening on the actual system. And then on the system itself, I've got all this data that I want to correlate to power. I've got some functions that I want to run, function foo and function bar, and I want to know which one is consuming more power, or if I optimize one, what it looks like when I optimize it. I want to find out where there's opportunities for energy savings. All these things require those two streams of data be integrated. We do that in PowerPack. So we take these hardware sensors and we get what I consider component level analysis. PowerPack is capable of basically integrating any sensor that's out of band with the stuff that's going on in band on the system. So we've done this with all kinds of different sensors. The ones that are interesting to power are usually the DC sensors. So we take a power supply, like an ATX power supply. We put some inline resistors between the wires and the component, like a disk drive or something. We measure the power across those resistors, and then we get that data. That's one stream of data. We do that for every rail in the system. We then reverse engineer which rails correspond to which components. We then take that data and correlate it to what's happening on the system. That's how it generally works. It's a lot of engineering, right? So it looks ugly when you do it, but it gives you some great data. And then on top of that, we have an API that allows you to basically embed calls to the measurement infrastructure from within your code, so you can see what's happening. Now you can do it system level if you want, but you can also do it at the code level. And lastly, what we really use it for is the analytics part of it, right? So that you can take the data, you can start making conclusions. You can start. There's no better way of getting power data than getting direct from the source, right? However, it is cumbersome, and so not everybody wants to do it. There are other ways of approximating it. So all the power models that we've done over the years, that other people have done over the years that I've seen, we can validate them, right? We can actually validate that these power models are accurate. If we just use performance counter data, for instance, we can validate that the models themselves are accurate. That's me. I show this slide for a couple of reasons. First, there's a couple of funny things about it. The second is that there's a supercomputer behind me. That's the SystemG Supercomputer. The G stands for Green. It's 325 Apple Mac Pro nodes, basically. It's fully instrumented. It has roughly 30,000 sensors, from thermal sensors to power sensors to everything. Every meter, every outlet, everything is censored. And we can use PowerPack to get data from that. The thing that's funny about this diagram is, first one is there's two mice, which I don't know why. There are two mice. And the second one is, look how serious I look. I should have been an actor because that screen is absolutely blank. And for some reason, I think I look smarter holding a pencil. At least that's what the photographer said. So this is the kind of data that we can get, right? This is showing you why CPU power management was all in vogue for many years, and still probably is to many extent. The CPU dominates the power pie here for all these different workloads, which go from idle to memory intensive, to CPU intensive, and to I/O intensive. Doesn't matter. Whatever you're doing, the CPU power dominates. The memory is the second biggest consumer, and for a long time, power supply was the third. Although the power supplies are getting more efficient, and we can see that. We get the power supply number because we measure both AC and DC power. So we measure all the power inside the box and then the power going to the wall, and we separate them. And that way we can tell you how efficient your power supply is. And it turns out that they're not very efficient. They actually waste quite a bit of energy. Okay. You can also do stuff like this, which if you've ever been to one of my talks on PowerPack, you've seen this slide. It is my FFT slide that I love to show, because it really shows you that for any application that you care about the functions and what power they're consuming, this will tell it to you. So this is time on the x-axis, this is power on the y-axis, this is CPU power, this is memory power, and the others, which are fans and disk drives and so on. And you can see, again, the CPU power dominates and memory is the second, and you can see that the CPU power varies with the load on the system. These are sends and receives. These are communication phases. So for a long time in power efficiency work, this was the focus. The idea was, why am I idling at 80 watts when I could probably idle at this isn't really idling, this is spinning, busy waiting on a communication, but it's basically idling. The CPU is not doing anything useful. So if it's busy waiting, spinning, why is it spinning at 80 watts? Why doesn't it spin at 10 watts, right? So the energy savings that we used to get, we still get, is basically from dropping that line down. If you leave the line up when it's here, you don't lose any performance. If you move it down during this phase, you don't lose any performance. All right, so this is where high performance power computing came from. The idea that you can save energy without introducing performance loss. So PowerPack is used by a lot of folks. You see here for lots of different reasons. I work closely with Texas A&M and UT on a couple of projects, so we use it together. Both Oxford and Berkeley both use it for algorithm analysis, and I'll show you a slide here from KAUST. So basically, you have a group of people that don't have any interest in doing the kind of systems work that we do, that want to use this stuff. So this is from Hatan Latif, who's now at KAUST, and Peter Luchak at Tennessee, looking at the different power and energy profiles for various versions of linear algebra subroutines. I don't have anything else to say about that other than I think these are really cool. You know, I was jealous many years, I don't know about you, when I go to application talks and they have the really cool 3D models and stuff, and I finally found something that we can look pretty cool for systems, right? So we try to use these graphs. These, if you see my talk, you've seen before, these are new. So we are, like many of you, working on an SC paper. This is a slide that's coming from, that has to be, so this data hasn't been analyzed very much yet. But basically what we've done is we've created what we call PowerPack 4.0. 4.0 has accelerator support, so it allows us to separate out the power consumption of accelerators like NVIDIA cards and Xeon Phis or the Intel Mic architecture. And what you can see here is basically the same graph you saw previously, but with GPUs, CPUs, and then memory and so on. And of course, the GPU dominates. The power profile changes dramatically when you introduce a GPU into the system. I have some more data that I'll show you during the panel that's different from this data that I think you'll find interesting related to this in terms of conclusions. Here's another interesting takeaway. This is data movement, right? During the data movement, the CPU is quite busy, actually, and it's consuming quite a bit of power, upwards of 40 watts each, right? So it's not so idle. And then the data movement itself, if it's long, it's wasting a lot of energy. So you could argue that this is all energy waste if you think data movement is energy waste. And these notions that data movement is a large consumer of power are probably true, although I haven't seen a lot of evidence other than this yet on it. I have another slide on GPUs. By the way, these are NVIDIA cards. This is sorry. For moving the data from memory to the GPU, basically. Yeah, it was. I think that was probably doing. I don't remember what benchmark. I think it was FFT from the. No, this is convolution from the SDK. Yeah.
On that previous slide, is the memory line is that the sum of two memory Grama?
No, this is just DRAM. Basically, okay. There's some more charts in the IEEE. I'll show them later, but they're in our IEEE computer piece from March. If you do Google that, let's see, show you a reference to that later. Then we also ported the API to GPUs, which is less than trivial, and so basically it allows us. It's supposed to be reminiscent of that FFT diagram I showed you earlier. It basically breaks down the different phases of the FFT from the shock benchmarks over. There's some gaps here because we haven't prepped this data yet, and we wanted to show these gaps. These are actually man-made gaps. We put these gaps in here. They should all be sort of smashed together, but if they are, you can't see as much interesting data. So, but basically, you can see, we can break down into functions. Now, you do lose some granularity. This is a good example of a trade-off between a measurement and performance. Is that if we do too fine-grained a measurement, we can actually perturb the results, and so we can't see what's happening inside this checks 12 phase of the application because it's too short. Basically, we introduce too much overhead in looking at it. So it's not perfect by any means, but it does give you a pretty good idea of what's happening. Right? So basically, you can go down to function level, but if you go inside, start doing measurements inside loops, you have the same problems you have with hardware counter data, which is that you introduce too much overhead. Yeah? This one is 0.02 seconds, right? So it's sub-second usually. It depends heavily on the instrumentation. We use National Instrument readers that are about $3,000 each. They sample thousands of times per second. But in this case, I don't remember why we don't have better granularity than 0.02 seconds, but there's a reason for it. It really just depends on the combination of the balance of how often we can sample, right? So and then how often we can do timestamps without introducing perturbation of the data. It's the highest rate we'll see. Nobody else will have this kind of data. I mean, PowerPack is unique in that way. The only thing I've seen comparable is a version that IBM did about 2 years ago. Implementing IBM can continue there. IBM actually took the same idea and implemented them as part of the power management infrastructure that they have today called Power Executive. It's now a band measurement system that comes when you buy a blue jean, I guess.
At that fine grained view, how do you maintain the synchrony between the clocks on the CPU and the power user.
That's a good question. We actually see a little bit of skew, and so we have a bunch of micro benchmarks that we do to figure out what the skew is on each system, and then we kind of assume that those don't change, and they don't really. I mean, we can keep running the benchmarks to recalibrate whenever we need to.
But we're going to have the skew, just that, smooth values are big.
We can do that hardware counter granularity, right? So we can take hardware counter data on the system, and we can take the fine grained power information and correlate them. Yeah. So that's how we do it. Other questions? So we took some of this stuff and we spun it out into the commercial sense. This is we took some of the ideas that we developed in PowerPack and implemented them in something called the Granola software, which was mentioned earlier. But this is just showing you that you can actually do. I used to have a number of other slides, but this is using hardware counter data is the wrong way to say it. This is using utilization data to predict power over time. This is a higher level granularity, probably once a second. But you can see that if you use a PDU meter, which measures things at once a second, and you use a software counter, basically, and then use a model coupled with the software counter, you can get pretty accurate data. But you have to have a meter ultimately to verify it. And we usually use the meters when we really are studying like systems development or optimization development, right? So. But it's a good fallback. So if you can only do hardware counter data or something similar, you can look at some of the models in the literature, and they do work. That's a prettier version that we use in the software. You could download it for free online. I'll show you another slide later that will give you a link to that. And then that brings me to modeling the effects power, which is kind of the topic for today. So what were we caring about? So there's some references there for you if you're interested. But basically, I'll show you two ways in which we try to get a better understanding of what's happening in the relationship between power and performance, and we use our toolkit to try to validate it. I won't go too much detail on this because I don't have a lot of time. But so the first question we were trying to answer is what happens to energy when we scale? In scaled systems and high-performance systems, what happens? And so we thought that at first we would look at Amdahl's law. And so basically, Amdahl's law says, if you don't remember, basically the execution time, as the degree of parallelism increases, the execution time decreases to a point, and then it sort of levels off. Whereas this is like the parallelizable portion, this is a sequential portion, and it sort of levels off from left to right. Nothing more dramatic here than simple application of Amdahl's law. So when we looked at that, we said the following. Time is proportional to energy. So the simple idea should be that if I decrease the execution time, I'm using power for less time, right? So then energy is power times time, and so the total energy used should decrease. If I do the same amount of work and I go from left to right, I will save energy. Basically, we're done, right? But the problem with this was I didn't explain. We were already empirically doing energy savings without hurting performance by using DVFS, right? We were basically, during those communication phases of the application, we were decreasing the power consumption of the CPU. Doing it for a longer duration, we would save energy. And we would do that without affecting the performance of the application. So what's wrong? Why doesn't Amdahl's law capture that behavior was our question. Because it does happen at scale, and it does sort of follow the same similar effects that you see in an Amdahl's law-like equation. And the conclusion that we found was that Amdahl's law ignores overhead. And if you look in textbooks like Kai Huang's textbook from the 90s and others, you will find this, that basically Amdahl's law says overhead is there, and it's an issue, but we're going to ignore it for the idea that we still get some benefit by just seeing the behavior of sequential versus parallel behavior as you scale. The problem for us was that it's the overhead where we get the gain, right? So it's in that hidden overhead that we actually see that we can reduce the power consumption of the CPU and not suffer the performance loss. Right? So how to capture that in an Amdahl's law-like equation? Well, that's what we call power-aware speedup. And the idea is that you basically think about Amdahl's law in two dimensions. Right? You think about it as the degree of parallelism in one dimension and the energy consumption in another, and that means that you have to capture the effects of overhead. So it all comes down to basically being able to quantify the overhead in parallel applications. And if you can do that, then you can estimate what the effects of the changes in power and the changes in parallelism at scale. Now that's the subject of a full paper, but the model looks like this, right? It's basically the similar as before, and it actually reduces to Amdahl's law when there's no changes in the power configuration of the system. But if the frequency, for instance, changes, then you have the sequential application of the code right, the sequential running, and the changes in frequency and its behavior over the parallel frequency with its changes in behavior for frequency, plus an overhead term, where the overhead term actually has to be estimated. We use a lot of modeling, a lot of analysis, and capturing performance data and everything to actually model this stuff. And when we're done, we end up with a curve that looks like this, where basically we can find the optimal operating points across the dimensions of processors and power, which in this case is frequency of the processor. So what you want is the minimization of that curve. Right? All right, I'm running low on time, but I think I'm going to make it. So the second question we tried to answer was how can we scale efficiently? So if I can change things in a system, we're pretty comfortable in our community with changing the number of processing elements and the size of the workload. And it's pretty easy nowadays to change the power configurations. If I have control over those three things, how do I scale efficiently? Right? What workloads do I, if I have a single application, I can change the workload size, I can change the number of processors, I can change the power at which all the processors operate. What's the best operating place? Where should I be operating if I want to do it efficiently? Well, we dug a little bit, and I found this paper that really inspired me when I was a grad student from Grama from Purdue, a school that you might have heard of. It's nearby. And Anand said that basically you have this concept of performance efficiency, and if you want to scale a code, one way to scale a code is to, I mentioned Purdue and it thunders. One way to scale a code is to try to maintain the same performance on a single node and then scale that same performance up. And so you change the processor configuration and you change the workload as you scale to try and maintain that sort of efficiency. And I thought that mapped really well to what we were trying to do, which is try and figure out what the configurations should be as we scale these things for energy efficiency. And we came up with a model that looks very simple, but underneath it's actually pretty complicated like the other one, where when you actually want to solve these equations, you have to get performance data from the system and so on, and energy data from the system to be able to solve them. But basically what you see here is it's the ratio of the energy. So you want to try to maintain a constant ratio of the energy of the single node case versus the multi-node case with the overhead once again. So once again, overhead has to be considered, just like we saw in the Amdahl's law equations. And when you do this, if you do it well, you come out with curves that look like this, also three-dimensional planes. And when you're looking for the optimal place to operate in, you draw lines like this. So basically, if you follow that line, it's a combination of power states, power states plus node size or scale, right, and workload. Okay, so that's why there are two. One is for two of those, and the other one is for the other two. So, but basically, the idea is that curves like this, the equation itself, will give you an idea of where you should operate if you want to scale the system, scale the workload, and scale the power states of the system. How you can operate roughly as close as you can get in your workload and your application, as close as you can get to what we call ISO energy efficiency. Okay. We use the same principles that you saw, the performance guarantee. We actually have some patents on what we call performance guarantee technology that basically allows you to operate power modes within a performance bound. And that's what's actually inside the Granola software. And I promised you I would give you websites if you want to download. The version you see there on the right-hand side is actually, I didn't say Purdue. The version on the right-hand side there is actually free. This is another new tool that we built called FlatPat, which is, I'm actually running on this system, which basically allows you to make changes in your battery configuration, and you see the effects of them. So here's an example. It's always dangerous to do a demo live, but I'll do it anyway. So what you see here is my FlatPat running here, and I've got 2 hours left on my machine, roughly. It shows me the projection of battery life that I could get. So if I dim my monitor, I would probably get more battery life, and my line will shift. And I can actually do that in real time. And so what FlatPat does for you is it provides a feedback loop for you, so that when you do something like change the brightness of my monitor. Oh, it's disabled. Sorry. When I change the brightness of my monitor, you actually see the effects of this. I have to pay for the pay-for version. I'm running the free version right now. When I want to demonstrate to you the ads, I have to run the free version. Let's see. And I'm on my last slide here. Okay. So where do we go from here? I'll talk more about what I think the future has in store for us and the problems that we're facing in the next talk, the panel. But I think the takeaways are that we need a lot of help, right? We because of what I said about the exascale, excuse me, we need disruptive versus incremental change. I don't know where that's going to come from. It's unlikely that it's going to come from one place, meaning it's probably not going to be a simple change in the architecture, or we're going to start using some quantum computing tomorrow and everything's going to be solved for us. The commodity matters. The commodity market matters. A lot of the early work that I started was very rooted in observing the commodity markets. The idea that we were going to see, I mean, it was not clear when I started the work in 2002 timeframe that we would see DVFS in servers. But the commodity markets told me that servers were going to be designed following the mobile systems, and that so you'd have families of processors that would carry over, and you'd see the same functionality in the commodity market for servers as well. And so the commodity market matters because it affects what we have access to, what we can do. In that way, the markets themselves matter. Tools matter. If you don't have the kind of tools that we have, it's very difficult to evaluate your work. You can use the hardware counter-based models, but there's always a little bit of concern as to whether you're accurate or not. We like to use the hardware meters because we know that they're accurate. Wanted major catastrophe. So one thing I like to point out to people is that despite how awesome I think our work and the work of the community has been over the years, I don't know a major manufacturer of supercomputers, except for the supercomputer in Munich, where's shout out to Martin. But except for the supercomputer in Munich, which uses turbo boost technology and allows it to run in the production environments, the first one I've ever seen that allows you to use basically dynamic voltage and frequency scaling on the system. All the rest that I know of disable it. That's because they don't know how it behaves. Or they don't know what it will do. Sometimes it will hurt performance. We have evidence of that. I'll show you that in the panel. I think the thing that I like to say about whether or not we'll make the 20 megawatt goal is that victory is inevitable when you change the game, right? So, so what I mean by that is like the goal has already moved, right? If I recall, the original goal was 2018 that we were supposed to have 20 megawatts, and then suddenly there were budgetary reasons it had to be 2019 or 2020. And suddenly we bought 18 to 24 months on the end of that. I wouldn't be surprised if that happened again if it didn't look like we were going to make it. So when people ask me, are we going to make it to 20 megawatts for exascale, I say yes, because we will either make it or we will change the game. Right? So that being said, thank you very much for your time. It was great.
Any questions? Yeah.
So when we move to the near-threshold operation, what do you think about this distribution change?
Can you repeat the question?
I think we're talking about the threshold. We're talking about at the microarchitecture level, the threshold makes it up, and the convergence of thresholds. So there's not enough dynamic power range. Is that what you mean? Is that your question? That's how I interpret it. That's what I want to know.
Well, I'm just referring to the use of the technology, the near threshold operation, the NDT actual. That will be employed in the new product. So when you use this technology, how will the service you mentioned for the FFT change and the distribution of the power change?
I'm not going to go more specific about the exact technology, and I think that what I would generally say is it doesn't affect us as much as you think. There was predicted that we wouldn't have dynamic voltage and frequency scaling now. They predicted that 7, 8 years ago. Still seem to have it. Turbo boost is pretty prevalent today. We predicted the end of threshold technology 7, 8 years ago as well. It's been predicted for a while. The reality is that these things need power to give you performance. Right? So as long as that's true, which I don't see that going away, unless we change to an entirely new substrate that we don't know exists yet, then you have lots of these things, and they will all consume a amount of power. Now, GPUs are a great example. GPUs triple the amount of power in your system oftentimes, right? I'll show you some data in the panel where in some ways you could argue the CPUs don't matter so much relative to them. And if we do go the route of GPUs becoming all we do, then it will be the GPU that matters. And I don't know that the threshold technology saves you there. So my point is that it will be something. Something seems to be always considered the power. And if it does change, all we do is change. I mean, there's reasons. There's a lot of different memories that are on the horizon. Memory is the second biggest consumer of power, so you could argue that if the CPU drops too much, then memory would be the thing we would target. We've done some work on power-aware memories, and there's a lot of things that change, but also ways you can go with that. So I think I'm eating in the next person's time.
We can take one last question. Someone has? Well, that's time to discuss the time. Okay. Thank you very much.
Thank you.